Hi everyone, it's Mr. H here for another video. This is all about proving trigonometric identities. We're going to look at the three identities on the screen there, but more than just solving those identities, I'm going to show you how to do it, why to do it, and some general strategies. This is a very important skill to have going into later years of high school and into university. So the first thing I want to establish is what an identity actually is. An identity is an equation which is true for all values of the variable. And so for each identity, we're not going to solve, we're not rearranging an equation, we're proving that the one side of the equation is equal to the other side. Now you might wonder, why is this useful? Well, in math, we often want to simplify things or write things in other ways because it helps us to maybe graph things better, maybe helps us to represent it better in an equation to solve something. And so this is a key component of upper level math and what you have to need to know to basically write things in different ways so that we can represent them differently. So here's our first identity. X plus 1 all squared equals x squared plus 2x plus 1. If we claim that an equation is an identity, we should be able to prove that it is. And so what we can do by proving that is first off, we take a little separation between the left and right sides of the equation. And so what you can see I've done below, and it's typed out in front of you, it says prove the identity x plus 1 squared equals x squared plus 2x plus 1. And so I'm going to take the x plus 1 squared and I'm going to expand that out. And so anything squared is that times itself. So x plus 1 times x plus 1 is x plus 1 squared. And then I go ahead and I multiply each term in the first set of brackets by each term in the second set of brackets. And I get x squared plus x plus 1. And then I combine the like terms, x plus x, and I get 2x plus 1, which is equal to the other side. Now, many of you who have been around math for some time and have been factoring recognize this is a perfect square. And you know that works. This is why it works. When you expand it out like I've shown, this is why it works. And so we know this is an identity in mathematics. Those two things give us the exact same thing. Now notice this is not a trigonometric identity. This is just an identity. It's an identity that shows how this works. Now let's get into the trigonometric identities because this is where their things are most important. Trigonometric identities are identities that involve trigonometric ratios. Some identities are true by definition. The reciprocal ratios are examples of this. Cosecant is 1 over sine. Likewise, and you can see them written down here in this chart, secant is 1 over cos and cotangent is 1 over tan. Other identities can be proven using definitions. For example, tan theta should say sine theta here over cosine theta. And so you can see that right here as this top middle one under the quotient identities. Cotangent is the reciprocal of tan, so that means that it's going to be cos over sine. And then we have last the Pythagorean identities. The sine squared theta plus cos squared theta equals 1. 1 plus tan squared theta equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. Now notice here it says to prove any of the identities in this table, we're going to use x, y, and r. I've taken these from a textbook that I'm using. Basically though, once you've proven these 8, we're going to use those as our building blocks to prove harder identities. We won't have to go and use x, y, and r after these 8, but to prove any of these 8, you should use x, y, and r. So let's see what that looks like in another example here. This example says prove tan theta equals sine theta over cos theta. I'm just going to make sure I have all this showing here in this question. To prove this, we use the definitions of sine, cos, and tan developed in an earlier lesson. You can go back to my video on 5.2 to see where I developed this. So sine theta is y over r, cos theta is x over r, and tan theta is y over x. And so if we're trying to prove this, then on the left side we have tan theta, on the right side we have sine theta over cos theta, and we need to break those down. So tan theta is just y over x, and then sine theta is y over r, and we're dividing that by x over r. Now remember here that if we have y over r divided by x over r, another way to write that would actually be this. And so we can then multiply that by the reciprocal. Notice I'm flipping that second fraction. in the line below, y over r times r over x, and what we get is we get the r values canceling out. And so we just are left with y on the top and x on the bottom, which is exactly what I had on the left side. So now we've proven that that identity is true. Now we knew it was true, it was one I gave to you, but still we want to get in the practice of proving them even if we know they're true. Now there's one caveat here that I want to add, and that's restrictions. You'll notice here it says, notice this identity has a restriction that x cannot be 0. Down here, x cannot be 0. Now you might think, well, what about r? Can't r not be 0 as well? Remember, r is the length of the terminal arm. So if we have something that we're graphing, and we have a terminal arm like so, then the y value is represented by how high above or below the x-axis it is. The x value is how far to the left or right of the y-axis it is, and the r value is the length of the terminal arm. That length of the terminal arm will never be 0. It's always got to be a length. So the r value is never going to have a restriction. Likewise, the y value here, if I just go back and circle those, the y value is only ever in the numerator. We can go 0 divided by something, that's allowed, but you can't go something divided by 0. So that's why the x value is the only thing that has a restriction here. So if x can't be 0, and we can see that that's related to the fact that cos theta can't be 0, then we draw a diagram to show, well, when is x going to be 0? Well, x is going to be 0 if that terminal arm is right along the y-axis. And if that terminal arm is along the y-axis, then really the y value is the same as the r value, and the x value is 0. And down here, the y value is the same as the, well, it's the same magnitude, but it's negative of whatever the length of the terminal arm is, because it's below the x-axis. And so we can see that that angle is 90 degrees, and the angle all the way around to here is 270 degrees. Remember, we're always measuring from the positive x-axis in a counterclockwise direction. And so those are the three things we want to get here. We want to get the fact that cos theta can't be 0, because we can't divide by 0 there. That x can't be 0, what that means in terms of x, y, and r. And then the angle, that it can't be 90 or 270s. There's three pieces to that, and then the diagram shows us why those angle restrictions occur. Now you might wonder, well, I thought an identity was true for all values of a variable. It is true for an infinite number of values of a variable, but it isn't always true for certain restrictions. We could literally put any other angle between 0 and 360 in here, and it would work. But we can't put 90 and 270. Take it as many decimal places as you want. If it's not 90 or 270, it will work, and that identity will be true. But it will not be true for 90 degrees and 270 degrees. All right, let's look at one other identity that is one of these 8 that is listed in the chart. It says prove 1 plus tan squared x equals secant squared x. Now here we have x instead of theta, but it means the same thing. It means the angle. The other thing worth noting here is that tan, let's just write these out as we start here, tan of an angle, the angles being x, is going to be y over x, the y value over the x value. So don't confuse the angle with the x value here, even though it's the same variable. I know it's a little confusing, but don't confuse those things. And then secant is the reciprocal of cosine, and cosine is x over r, so that means secant is r over x. So let's go ahead and separate the left side and the right side and prove this here. So 1 plus tan squared x is equal to 1 plus, well, what is tan of x? Well, tan of x is y over x, and that's squared. On the right side, I'm just going to draw a line down the middle to keep these separate because we don't want to rearrange anything. We simply want to show that one side is equal to the other. So on the right side, we have r over x all squared. So if I go ahead and I work a little bit further with the left side now, what I'm going to get is 1 plus y squared over x squared. And then on the right side, I'm going to get r squared over x squared. Now, at first glance, it doesn't look like we can get things to be the same, but what do we know about adding fractions? Well, in order to add fractions, we need to have a common denominator. Right now, that denominator of the left side is 1 over 1, so the denominator is 1. So what I need to do is I need to multiply by x squared over x squared. That still keeps that fraction as 1. and I'm left with x squared plus y squared over x squared. So I can write everything over the same denominator. And you can see here that now I have x squared in the denominator, just like I have over here, and I have one fraction. It's important to keep in mind that when we're graphing things, and I'm just going to graph this here off to the side, when I'm graphing something, I have an x value, a y value, and I have an r value. Remember that that is always applying to a 90-degree triangle, like so. Well, what does that look like to you? That looks like the Pythagorean theorem, doesn't it? X squared plus y squared equals r squared. That's always going to be true. So what this means is that this is equal to r squared over x squared. That's exactly what I have on the other side. So therefore, the right side is equal to the left side, and we've proven that this is true. Don't forget restrictions, though. What about the restrictions? The first thing I want to do with restrictions, if I can spell the word properly, with restrictions, is this. I want to recognize that x can't be 0. It's the only thing that's ever in the denominator, right? So x cannot be 0. Well, what does that mean? Well, it means when I go to my graph that it can't be 0 at the same things I did before, right? It's going to occur right there and right there at angles of 90 degrees and angles of 270 degrees. So that means our restrictions are that x, I shouldn't confuse that with theta here. The x is what I'm using as my angle here. X cannot be 90 or 270 degrees. So I figure out what's the restriction on x, y, and r. I draw my diagram, and then I list my restrictions in terms of the angles. And that's now complete. So those are how we prove those 8 identities. We use x, y, and r. As soon as you have anything beyond those eight identities, we want to use those 8 identities as the building blocks. And so it's very important that we have these understanding of factoring in order to go into these next types of proofs. So 1 minus x squared. Well, that's a difference of squares. This can be written as 1 squared minus x squared. Well, if you know your difference of squares, that's 1 plus x times 1 minus x. Well, what do we do now when we move to part B here on the right? 1 minus sine squared theta. Well, hopefully what you recognize is, well, that's the same thing as 1 squared minus sine theta squared. Might be helpful to see that in brackets. Well, that's also a difference of squares, right? Because that's 1 plus sine theta times 1 minus sine theta. Now you might stop me for a second and say, well, what happened to the left side and the right side? Remember what we're doing here is we're just developing the factoring skills that are going to help us to prove identities in the future. All right, so we're not doing any left side or right side. We're not doing any restrictions. We're just trying to learn how to factor with sine, cosine, or tangent. So let's look at another example here. X squared minus y squared. Well, again, that's a difference of squares. X plus y times x minus y. Done. Well, what about this next one? Well, I could rewrite this as sine theta all squared minus cos theta all squared. Well, that's like x squared minus y squared, right? And so that's sine theta plus cos theta times sine theta minus cos theta. Look at the part C and see how that's similar, right? At any point, if you wanted to, you could say let x be sine theta and y be cos theta. Then you get what's on the left on part C. You factor that to get x plus y times x minus y, and then you can sub back in sine of theta for x and cos of theta for y, and you get the line that we have at the end of part D here. So you could do that at any point to help you out if you don't see this intuitively. So we've done 2 difference of squares examples. Well, what's this next one? This next one is a perfect square. How do we know it's a perfect square? Well, it's the first term squared minus 2 times the first term times the last term plus the last term squared. That is the very definition of a perfect square. And if you get that, what we get is we get x minus, it's always the same sign as the sign before the second term, minus 1 all squared. It's the a term minus the b term. And so it's x minus 1 squared. It's a perfect square. Well, what do we get if we have cos squared theta minus 2 cos theta plus 1? Well, notice that the cos theta is like x. Same thing. And so if you see that right away, you could totally go ahead and solve that directly. But if you don't see it right away, what you could do is this. You could say let x equal cos theta. And if you let x equal cos theta, then we get the fact that it's equal to x squared minus 2x plus 1. Well, now we can go ahead and factor that, just like we did in part E, x minus 1 squared. And now what you can do is you can sub cos theta equals x back in. And so if we get that, we get cos theta minus 1 all squared. Did you have to sub in x and then put cos theta back in? No, you don't have to do that. But if you're not seeing it and you can't factor it without an x or a y in it, go ahead and change just let the cos or sine or whatever's in the equation be equal to a variable and factor it and then put it back in later. And then we get, in this case, cos theta minus 1 all squared. So there you go. Those are some good strategies for factoring. Well, what are some other strategies that we're going to have? Let's see. This can be a very challenging thing to do. And so proving identities takes a lot of practice. In general, here are the strategies I recommend using. Try simplifying the more complicated side first. Express all ratios in terms of sine and cosine. If you see a tan, make it sine over cos. Use the Pythagorean identities. For example, sine squared theta plus cos squared theta. Replace it with 1, or maybe a rearranged version of that identity. If you see 1, sometimes it'll be helpful to put sine squared theta plus cos squared theta in for it, for example. Another strategy is combine fractions which are added or subtracted by finding a common denominator. And then factoring, just like we did above, that's a very, very, very helpful strategy. So that's the strategy that's going to come into play in this example, the last one we're going to look at in this video. So this example says this: prove sine squared theta over 1 minus cos theta equals 1 plus cos theta. So we separate that, the left side and the right side, and we go ahead and we see how this works out. Now you'll notice that we don't have any denominator on the right side, which tells me I somehow want to cancel the denominator out on the left side. Well, how do you think I could do that? I did tell you that this was a very useful identity and would be coming up a lot. What we can do is we can rearrange that identity for sine squared theta. If I rearrange it for sine squared theta, I get 1 minus cos squared theta. I'm just subtracting cos squared theta from both sides. So what I can do is I can replace sine squared theta with 1 minus cos squared theta. 1 minus cos squared theta. My pen will work there. 1 minus cos squared theta. If I divide that by 1 minus cos theta, some people initially think, oh, I can just start canceling things out. Not too fast. Because what we did earlier is we did some factoring. And this is a difference of squares on the top. So before I cancel the 1 out with the 1 below, I need to factor it fully first. Because I can't cancel if I'm adding or subtracting things in the numerator or denominator. Only if I'm multiplying. So I'm going to make this be 1 plus cos theta times 1 minus cos theta. It's just like, if you have to, you can go back and do the 1 minus x squared. Well, that's 1 plus x times 1 minus x. And then you can put cos theta back in for those. And you can see it's 1 plus cos theta, 1 minus cos theta. And that's all being divided by, don't forget your denominator, 1 minus cos theta. Well, now I have factors in the numerator, and that factor is exactly the same as that. In other words, we're saying 1 minus cos theta over top of 1 minus cos theta. Well, that's just 1. So we can cancel those out. And what I'm left with is 1 plus cos theta, which is equal to the right side. But don't finish too soon. Don't forget your restrictions. That's the last thing we have to do. The restrictions. Well, what are the restrictions? We have here that 1 minus cos theta cannot be equal to 0. This entire denominator right there can't be equal to 0. Well, if I rearrange that, I get that cos theta cannot be equal to 1. Well, this is a little more complicated than ones we've seen before, because before it was just 0. Well, what is cos theta equal to? Cos theta is, in terms of x, y, and r, it's x over r. So if x over r can't be 1, that means that the x value cannot be equal to the r value. I've just multiplied both sides by r. Well, when is that going to be the case? When is the x value going to be equal to the length of the terminal arm, the r value? Well, that's going to be right there at 0 degrees, right? Because the length of the terminal arm is r there, and the x value is all the way out to the end of that. Now, some people think, well, what about over here? Is that not going to be the same? Well, out here, the r value is still positive, but what's the x value if you're over here at 180 degrees? That's a negative value. That does not apply. So the only place this has a restriction is at 0 degrees, and then again at 360, 720, etc. But if I'm trying to say between 0 and 360, I'm going to say that theta cannot be equal to 0 or 360 degrees. I'm going to have a later video that you can check out that will show you more all about how to do this in more detail with more difficult questions. But there you go. That's the basics of how to prove trigonometric identities. If this video is helpful, be sure to give it a thumbs up and please consider subscribing.